Okay, some assumptions of the t-test. Two basic assumptions are necessary for a hypothesis test with t. The values in the sample must be independent observations. In everyday terms, two observations are independent if there's no consistent, predictable relationship between the first and the second. More precisely, two events are independent if the occurrence of the first event has no effect on the probability of the second. So that's one caveat. The population sampled must be normal. The assumption is a necessary part of the math underlying the development of the t statistic in the t distribution table. Violating this assumption has little practical effect on the results obtained for t, especially when the sample is relatively large. With very small samples, on the other hand, that normal distribution is important. So anyway, these are caveats. I might throw them in as extra credit on the test, but there are just two major assumptions of using that t-test. So what else influences t obtained? Well, one thing is the influence of sample size and, of course, the sample variance. And where are we getting that from? Well, right here. Here's my estimated standard error. And that, of course, is the denominator term of t. When this value is large, it tends to make t, what would it be? Smaller, right? For instance, what's bigger, 1/2 or 1/8? Is it 1/2 bigger than 1/8? When I blow up the denominator, it makes t smaller. Now, what can make this bigger to make t smaller? A lot of spread. If there's a ton of sample variance, that means the sample standard deviation will be larger. So if I have a tremendously variable sample, it undercuts t. The researcher would prefer to have a sample that's less variable, because walk through the process. If this is large, this whole thing is going to be large. If this whole thing is large, then t is going to be smaller, because 1/8 is smaller than 1/2, for example. What about n? If n is large, what happens to the estimated standard error? It gets smaller. If I've got 144 down here instead of 4, makes a big difference. 144 is going to make this a lot smaller than 4 would. If this is very small, what does it do to t? It makes it larger. Again, the example. Wouldn't I prefer to have 1/2 than 1/8 of a pie, let's say? If this number is very small, t gets very large. And what would make this entire thing get very small? A very large n here. You just sort of walk through the math. So what influences t obtained? That estimated standard error. Because the estimated standard error appears in the denominator of the formula, a larger value for the estimated standard error produces a smaller value for t. Any factor that influences the standard error also affects t, or the likelihood of rejecting the null. The two factors that determine the size of the standard error are the sample variance, or the standard deviation, and the sample size n. The estimated standard error is directly related to the sample variance, so that the larger the variance and the larger the standard deviation, the larger the error. Thus, larger variances and larger standard deviations mean that you're less likely to obtain a significant t. It undercuts it. In general, large variance is bad for inference. Large variances means that the scores are scattered, which makes it difficult to see any consistent patterns or trends in the data. Conversely, the estimated standard error is inversely related to the number of scores. The larger the sample, the smaller the error. It kind of almost makes sense experientially. All other factors held constant, large samples produce bigger t statistics and therefore are more likely to produce significant results. For example, a 2-point mean difference with a sample of 4 may not be convincing evidence of a treatment effect. Of course, that sample of 4 could have wound up that way by chance. Much more likely with a sample of 4. However, that same 2-point difference with a sample of 100 is much more compelling. It just makes me much more convinced, and the math tends to bear that out.